So now this is recording. So good evening, everyone. Today we are in the week 8. So of this fundamental of theoretical and experimental aerodynamics problem solving session. Instructor Professor Arnab Roy and myself Gangadhar Venkatraman. And today we will see a few more problems that we left in the week 7, and then we will see some problems that related to finite wing airfoil concepts, and then we will see some more problems related to those concepts. And then before starting this session, Arhit or any other, you have any doubts, you can just clear before starting this, and then we can move on to the concepts.
No, sir.
Aditya.
No.
Okay. Okay. So, if no doubts, let me start today's presentation. I think it is recording. Yes. Okay. So now, in the last week, we have discussed a few problems that are related to potential flows, kind of flow fields that we discussed in previous lecture. Discussed in the previous lecture, and these are the some questions that we discussed in the last session. We discussed some queries from you, and also Professor had discussed many of your questions that you guys have posted in Google Forms through the NPTEL portal. So in the last, in the Wednesday, he answered many of your queries about good queries also in the live session of the Zoom meeting that you can review, or you can go through those the recording live session so that you can get clarity of what are your actual doubts, and how you frame the questions, and what are the possible solutions from your question to your questions. So that is also useful for your learning. And these are whatever the screen content that you are seeing, that these are few questions that we solved in the last week. So in this week, let's continue our discussion or let's continue our solving session by solving a few more problems. And we have a question number 7 here. The question number 7 from the last session that we stopped. Let's read this question. In this question, we have that a Douglas DC-3 aircraft, and it is having it has a 1.848 feet thick airfoil with 15.4 feet of chord length. Its thickness. Let's write the details of it. It has a thickness. Just a It has a thickness equals to 1.848 feet, and its chord equals to 15.4 feet. See, these all units are in the feet. It is all in the same system of units, so we don't need to bother about while we are going to do any kind of substitution or using any kind of formulas. So the maximum camber is 0.462 feet. Then location of maximum camber. Location of maximum camber is at 7.7 feet. Okay. Then what will be the correct nomenclature for the airfoil using an AGA 4-digit series? So we have some options that is representing an AGA 4-digit series. We need to calculate what is this corresponding to. What are these details given here are corresponding to which of the airfoil, or maybe none of the above also. So let us calculate using these details. Let us find out what kind of NACA 4-digit series 6. It is very clear that it is because it is having a maximum camber and location of maximum camber. It is asymmetric or cambered aerofoil. We can say cambered aerofoil. And the thickness we can see 12% is clear. The thickness is the last two digits of the aerofoil. You say NACA A, B, C, D are the 4 digits. The last two digits give you the percentage of thickness. So we only need to look at what is the uh, like in simple way to find out the things directly from the options. We only need to look at whether this one. This is I am telling in the perspective of solving a question directly without looking at the more details. We already got it is a cambered aerofoil, and we already know two things like it has a thickness either 12% or none of the above. And another thing that we can look at is whether it has odd location. This is a maximum camber location. The second digits, the letter B or the second digits of NACA 4 series will indicate location of maximum camber in respect to the chord. So to find the location or maximum camber, let's see uh, the third digits how it can indicate the location of maximum camber is how much in terms of the overall chord. That is 7.7 feet is the location of maximum camber divided by 15.4 will give you a 0.5 C chord. That is, this letter is corresponding to 5. If you multiply with this with a 10. So the value is, the second digit value is B equals to 5 that we got. That is 5 corresponding to option C. But still, to understand the complete details of this question, let's calculate the thickness also, thickness and maximum camber also, because we need to verify whether it is none of the above also option is there. So we need to verify all the possibilities of whether it can be 3, 5, 1, 2 or whether it is none of this. So we already got the answer whether it can be a NACA 3, 5, 1, 2 or it is a none of the above. So between these two options, let's check by using the thickness first. We have thickness given as 1.848. If you divide it by the chord, that is 15.4, you will get the thickness equals to 0.12 C. That is C represents the chord. Okay. Then if you multiply it with 100, you will get 12. So CD equals to 1 and 2. So it is all the details like 5 and 12 are common, but we have to also find out the maximum camber. Maximum camber is given as 0.462. If you divide it by what is the value of the chord? 15.4, you will get 0.03 C. Okay, 0.03 C means if you multiply it with 100, you will get 3. That is A value equals to 3. So with this, the airfoil is NACA 3512. Okay, so this is how we can find out with the given data where what is the nomenclature of the corresponding airfoil. And if it is 5 series, we will get a additional something like design lift coefficient and those kind of parameters will come. But the NACA series nomenclature, using this nomenclature itself, we can generate the airfoils. Maybe in the some kind of tools, I will just recommend if you want to see this kind of how NACA 3512. We know this is the nomenclature that designates an airfoil. Whether but how it looks like the entire airfoil, if you want to see, I will just suggest that you can go to this website, airfoiltools.com. You can go to this website and you can just find out this, or you can use the boxes there or the input boxes. There you can type for the NACA 3512 aerofoil and you can visualize how it looks like. Okay. So this is one of the best website for generating the aerofoils that generally use. And let's go to the next question. In our next question, we have for an aerofoil at alpha equals to 4 degrees, given that alpha equals to 4 degrees, CL is 0.55. It is a non-dimensional. You should remember the CL lift coefficient is a non-dimensional parameter, and CM is negative 0.006. Okay, and the zero lift angle of attack is minus 1.2. Also, at alpha equals to minus 5 degrees, CM at quarter chord point. This represents a quarter chord point, and that is corresponding to minus 0.0135. Okay, now determine the location of aerodynamic center. This kind of similar problem we also solved in our past lecture or past sessions, but this let's also solve in a similar way, that to find out this aerodynamic center, what we need to do. We need to do first calculate we need to use its definition, the definition of the aerodynamic center, that is dCm by d alpha about the aerodynamic center is equals to 0. This is the definition of the aerodynamic center, where the moment coefficient about the angle of attack, the change of moment coefficient with respect to the angle of attack at a point is equals to 0. At this point, we say it is a called as aerodynamic center. Just give me a minute. Just a second. Okay. Sorry for that. And now we got the definition of aerodynamic center. If we let's write the given data. We have 4 options here in our given data. We have angle of attack alpha equals to 4 degrees. This is corresponding to CL equals to 0.55. Okay, and alpha equals to minus 5 degrees. We have CM equals to, or CMC by 4. It's at a quarter chord point, that is CMC by 4 equals 0.0135. Okay, now what we need to do is we need to determine the aerodynamic center. Also, we have additional information that here CMC by 4, here at this alpha equals to 4 degrees, we have CM C by 4 is equals to minus 0.006, right? Okay, and the zero lift angle of attack, that is where your CL equals to 0, the corresponding alpha is equals to minus 1.2 degrees. Okay, and these are the given details. So using this definition, when we formulated that what is the aerodynamic center value, what is aerodynamic center formulation, and after applying this definition of derivative, we got that aerodynamic center in non-dimensional format, that is XAC equals to, let me write that. We got this formulation, that is XAC equals to minus M naught by A naught plus 0.25. This is the equation we got for aerodynamic center when we apply this kind of definition for a moment coefficient. Okay, so let's use this. In this equation, if you see, you have 2 parameters, that is M naught and A naught, where M naught is slope of the moment curve, and A naught is slope of the lift curve, right? So to find the M naught and A naught, we can use the given data. Let's first try to find out the M naught. We have that M naught at 2 different angle of attacks, that is M naught at 4 angle of attack and M naught at 5 angle of attack. So that is minus 0. This is yeah, M naught is the slope of the moment curve. That moment you should take at CMC by 4. Okay, that is minus 0.006 minus of CMC by 4. This one is minus 0.0135. So I'm doing the difference of CMC by 4 at 4 angle of attack and -5 angle of attack. So the corresponding angle of attacks are, I will just write in another way, that is CMC, for your understanding, CMC by 4 at the location 2, or the final, I can say final, this is final or location 2, and minus CMC by 4 at initial by alpha final minus alpha initial. This is the way that we generally find any slope of a curve using the initial data and the final data, or you can take any 2 points on the line. So with the data we have, I'm taking the 4 angle of attack and -5 angle of attack. So this will be 4 minus of -5. We should use the sign convention correctly. So once we apply the sign convention, you will get m naught equals to, let me write this, because we are doing with the degrees directly, we are substituting the degree values only. So you should keep on that, keep in mind that m naught equals to, that we are writing in degrees, m naught equals to 8.334 times 10 to the power -4 per degree. Okay, or I can write it as a per degree. Okay, once you are done with this m naught, you can now find out the a naught values. Let's find the a naught value. A naught equals to, in the same way that we did for m naught, now also we can use, but a naught we have at CL, that is a naught corresponding to the CL lift curve slope. So initial CL, final CL, you can take it as CL, that is corresponding to angle of attack 4, that is your final 0.55 minus 0. This 0 corresponding to angle of attack of -1.2. Okay, so and then you let's apply the same angles, like the angles that is corresponding to the CL that we took are -1.2. If you simplify, if you solve this, we will get a naught equals to what we will get, yes, 0.1058 per degree. Okay, this is what you will get. -5, don't we have CMC by 4? So 0.035, yes. So everything we have ready now, that is 0.1058, and then m naught equals to 8.38334 times 10 to the power -4. These things are readily we have. We can just substitute in our XAC equation, that is XAC equals to -8.334 times 10 to the power -4 by your A naught is 0.1058. Why we are substituting these values directly in per degrees? Because we are doing a ratio here. In this ratio, whether you substitute in per degree or per radian, the ratio will not change. So it doesn't matter. And then if you simplify this, you will get XAC equals to 0.2421. In terms of chord, it is XAC equals to 0.2421 times C. So this is your aerodynamic center. Okay, this is corresponding to your question. In this question, the option is B. So this is how you can find out your aerodynamic center. So let's move to the next question. So in this question number 9, we have, for a non-lifting potential flow, we have a potential flow here. Let's write all the given conditions very clearly. This is a non-lifting potential flow. That means there is no vertex here. Flow past a circular cylinder. You should remember that if it is something like a non-lifting potential flow, means there is no circulation. You can write the statements clearly. There is no circulation or the vertex imposed. There is no circulation or the vertex that you are imposed on the flow field. Okay, for a non-lifting potential flow past a circular cylinder, and the question is, at what angular velocity? What is the angular velocity the surface pressure on the cylinder, will be equal to the free stream surface. So the question is like this. I have a non-lifting flow over a cylinder, and I need to identify the pressure distribution from the theory around the cylinder. The flow is uniform flow. Uniform flow U infinity or V infinity, you can say, and it is having some radius R, and you are moving in the direction of anti-clockwise direction that's corresponding to theta. It is a polar coordinates kind of system. So the question is, at what locations, what are the angular locations, not in the radial locations also, what are your angular locations for this potential flow? The pressure on the cylinder will be equals to the piston pressure. So if you are allowing the U infinity onto the cylinder, that's corresponding to some particular pressure, the piston pressure, that is P infinity. So we need to find out some points at which, some point P, at which this P infinity is equals to the local pressure of cylinder. So to get a more clear understanding that, let's write what we know on cylinder pressure distribution function. We found that from our theoretical understanding that Cp, or the pressure distribution on the cylinder non-dimensional way, is equals to 1 minus 4 sine, let me write this equation correctly. Yes, 1 minus 4 sine square theta. Sorry, 1 minus 4 sine square theta. So this is the equation that we have for pressure distribution on the cylinder. And another formal definition, the first clear definition of the Cp is P minus P infinity by half rho V infinity square. Okay. So this is the formal definition of Cp, that if, but our question is, we need to find out the locations where this P and P infinity are equal. If this P and P infinity are equal on some point of locations on the cylinder, that means the Cp is equals to 0 at those points based upon this formal definition. So we need to identify the locations where Cp is equals to 1 minus 4 sine square theta is equals to 0. These kind of locations we need to identify. So if we solve this, what we will get? We will get 4 sine square theta equals to 1, and that will be sine theta equals to 1 by 2. Okay, so sine theta equals to 1 by 2. This is plus or minus because we are converting from a square to root. So the solution when the sine is equals to plus or minus half, is the solution will give, if you looking at from at 0 to 360 degrees, your solutions are like this: pi by 6, 5 pi by 6, 7 pi by 6, and 11 pi by 6. These are the possible locations where you will get your Cp is equals to 0, or the P stream pressure is equals to the local pressure on the cylinder. Okay, let's go to the next question. Yeah, we have two solutions possible here: 5 by 6, 5 pi by 6. Okay, yes. So let's go to the next question. In this question, we have let's see the question. Miss Windy is standing at a location 6 meters away from the eye of the vertex, where she is sensing wind blowing at a speed of 160 kilometers per hour. Determine the strength of this vortex. So some person at 6 meters away from the eye of the vertex, say this is a vertex origin here, and this distance is about 6 meters. So from the origin, we are having the 6 meters of distance, and the velocity v infinity here, or v, is can be written as 160 kilometer per hour. Now we need to determine the strength of the vertex. If the vertex is inducing some velocity at this point, we can write based upon this formulation that angular velocity induced by vertex is v theta equals to minus gamma by 2 pi r, where r is the distance between the origin or the eye of the vertex to the point where we are calculating the velocity, or where we are feeling where this person is feeling this velocity. So let's see its velocity. What will be circulation? But this circulation that they ask, the strength of the vertex is hidden in this value, that we denote with the capital gamma, and this is the strength of the vertex. So let's see. So all these things are we know that v theta 2 pi r, everything we know. Once we solve that, let's substitute this minus 160 into 5 by 18, that we need to convert into the meters per second from the kilometers per hour to the meters per second, times 2 pi times 6. This 6 is the distance between the origin to that particular point. So once you substitute all these values, you will get the gamma equals to minus 1675.52. The units are, you must be careful what is the unit. Sometimes you may also get a questions on what is the unit of particular quantity in aerodynamics. So 1675.52 meters square per second. So this is the value, and it is corresponding to option A. If you see that, if you take the absolute value of this strength of the vertex. Okay, let's go to the next question. So in this question, we have that which option is correct for the following? Sorry for the this. Okay, we have that which of true or false kind of statements. Let's read the statements. According to the Kutta condition, the strength of the vertex sheet at the trailing gauge of an aerofoil will be infinite. This is directly from the. This is not at all the Kutta condition. So the first statement is wrong. And the second statement, according to the Kelvin circulation theorem, the time rate of change of circulation around the closed curve consisting of same fluid elements is zero. Yes, from the Kelvin circulation theorem, we have d gamma by dt is equals to zero, the substantial derivative. You should trace the circulation with the same fluid particles that you are looking at. So the first statement is false and the second statement is true. Okay. So the next question is, so this is our next question. In this, which option is correct for the following statements? Again, it is true or false kind of statements. Just a minute. Okay. And the statement one, we have for a symmetric aerofoil, the center of pressure and the aerodynamic center coincide with each other. This is true. The parasymmetric aerofoil, for most of the angle of attack, in the linear, at least in the below the stall region, you will get the aerodynamic center and the center of pressure coincides with each other. First statement is true. For a symmetric aerofoil, center of pressure and aerodynamic center are located at the half chord. This is not a correct statement. So this is the answer for your uh, this question. And do we have any other questions? I think this is the end of this slide. Yes. So these are the questions that we left in the last session. So if you have any queries up to this, we can discuss, Arhit, or any other. Okay, if no queries, we can. Arhit, you have any queries? I cannot hear you. Okay. If no queries, we can move to the next, some few concepts, and we can move to the next session, next presentation. Let me open this. Yes, Arhit, you have any queries? I'm unable to hear you.
Sir, am I audible now?
Yes, you are audible now.
Sir, in that last PPT, in the last slide, if it was written the quarter code, then would it
Hmm.
be correct, sir? Because, sir, in case of cambered airfoil,
Okay,
in,
completed. In case of cambered
yes, sir.
aerofoil. So in case of cambered aerofoil, it is not be the same thing. But here the statement is clearly given that it is a symmetric
Symmetrical.
aerofoil.
Yes, sir.
So according
Symmetrical.
to the symmetric airfoil, it is true. But if it is a cambered aerofoil, it may not be true. The aerodynamic center and the pressure center of pressure will be different. Okay.
Okay, sir.
So let's discuss some of the contents that on which we are going to see some problems for the today's session. For the finite wing airfoil kind of conditions we are going to discuss today. So in this discussion, we will see from few lectures, a short notes that we need to take up from the lectures of professor for understanding this finite wing concepts. Suppose you have a finite wing and the airfoil cross section is something like that. You will see uh, wingtip vertices induce some kind of drag because of the induced angle of attack. If you write this is an let's say your geometric angle of attack is alpha, this one, and because of your induced angle of attack or because of the wingtip vertices, there is angle of attack decrement because of that wingtip vertices in the local to the chord. It is not like with respect to the chord we are seeing like at every point on the surface, the local angle of attack varies. That is alpha effective and the decrement we say is alpha induced angle of attack. The corresponding change or the lift direction because of this induced angle of attack alpha I will create a component of the drag that is di. This is the induced drag we call induced drag and induced angle of attack. Okay. So how it is happening? How it is happening? We know the theory of it, but few points that we need to mention that flow curls from the bottom of the surface. If I take an aerofoil, the flow curls from the bottom of the surface like this, from both the sides. These are called we call as the wingtip vertices. So these we call as the wingtip vertices. Okay. So in this, what happens is the flow from the bottom surface curl on top of the upper surface and moves along the span. That is also creating additional para phenomena called upwash and the downwash. Because of this downwash on the top surface, we are getting a change in the angle of attack. That is alpha. If it is your geometric angle of attack, you will get a effective angle of attack. That is by subtracting the induced angle of attack due to this downwash from the geometric angle of attack. Then you can write this effective angle of attack is equals to geometric angle of attack minus induced angle of attack. And the lift also decreases, and the corresponding additional component we will get as a induced drag. So these are the three things that you must remember what happening in the finite case, finite aerofoil. And we called some kind of drag is there. That drag we generally call as profile drag. Is a combination of pressure drag and skin friction drag. Combination of these two is called profile drag. We also additionally have wave drag, which airfoil or the object experiences when it goes in a supersonic kind of speeds. And we also get induced drag, that what we have been discussing because of the wingtip vertices. So these are the different types of drags, and so these wingtip vertices alters your velocity distribution or the pressure distribution on entire your surface if it is sufficiently less length. The span is less as with your compared to your chord. So this is your chord. If you say, if this is my chord length and this is my span, if this chord to span ratio we called aspect ratio, the formal actual definition of aspect ratio is b squared by s into c, that is the square of the span by sorry, b squared by, yes, the surface area of the, this is b squared by s, sorry, let me, this is b squared by s, where s is the surface area of your plane form area of your aerofoil. If you can further simplify this, b squared by bc, and you will get b by c. So this is how the aspect ratio is defined. If this aspect ratio is small, like in compared to your chord length, then your wingtip vertices severely affects your flow on the aerofoil. If it is sufficiently long enough, so wingtip vertices cannot move on the entire of airfoil surface, and its effects are less, and it almost acts like your two-dimensional aerofoil or infinite span kind of aerofoil. So aspect ratio effects are very crucial while we are deriving the lift and drag coefficients on the aerofoil, even for the experimental perspective or in the numerical perspective. So another thing is higher aspect ratio can match the characteristics of finite wing with the airfoil. That's what we discussed. Another important thing that we need to discuss is, suppose if you are having a wing root here, and sorry. So this root chord, we say it is larger than this your tip chord. This chord we say is a CT, chordate root is a CR. So the ratio of CT by CR we called as taper ratio. You provide a taperness to your wing, then it is called the taper ratio. And if you plot a mean line along the quarter chord position, and if you see the same with respect to the horizontal line, there is a swept back. The wing is inclined to your horizontal. Suppose this is your horizontal line, and wing is inclined to your horizontal, and you just drawn this line along the quarter chord position. Then this angle is is called swept back angle or swept angle. Okay, so these two are also important parameters. And then for modeling this finite wing kind of concept, we are taking a vertex filament, and this vertex filament, it is from Prandtl's lifting line theory. So we are taking a single vertex filament that representing this straight line, this horizontal straight line is for your modeling the bound vertex, that Brandles from this is a question that Harith we already discussed like from your earlier doubt that why the Brandle lifting line theory on the wing is stating that it is similar to the bound vertex. That the idea is the finite wing in the Brandle theory is that the finite wing is similar to the bound vertex for modeling. So that's how the Brandle started assuming, and then he formulated the theory of this finite wing lifting concepts. But since your vertices or the vertex filament, you cannot stop in the flow field. If once it is, if you cannot take a small particular length kind of filament, you need to take an infinite span. So if you are having an infinite span, then these two remaining or ending up in the flow field by making it as a wake in the flow field, these two remaining kind of structure. So this line is for the bound vertex, and these two are for will model your trailing edge vertices. These two are modeling for your trailing edge vertices. And if you consider any point on this vertex filament and from the mean location, say it is your y equals to 0 where your origin locates, and if you are moving to the left and right, the y changes from positive to negative. And then this is your b by 2 plus y. If you stay up to this location, and this is your b by 2 minus y. Okay, so this is the starting phase and how this bound vertex and wing trailing edge vertices are used to start this lifting line theory. And then once they started this, we ended up with the solution like the velocity in the downward direction that can be formulated by this is a downwash, that is velocity w of at any location that the downwash present at that particular location y. We got that the strength of the vertex, that is gamma. If it is a single vertex filament, its strength is common everywhere. Arhit, are you able to hear me?
Yes, sir.
Okay, okay. Just disconnected. Okay, if you are able to hear me, then that is fine. Okay. So the downwash is W of y that we get, the minus gamma by 4. And then the complete thing is like this. For a single vertex filament, my b by 2 whole square minus y square. This is the velocity that is inducing at that particular location W uh, because of the single vertex filament. Um, Then the idea is then change it to more number of vertex filaments to change the circulation in such a way by any kind of generalized formulations. Like the generalized formulation involves the Fourier coefficients that I hope you are able to understand what I'm trying to convey you, that generalized circulation coefficient, that what does it mean, that you are placing instead of a single vertex filament that not completely modeling your requirement, you are now placing a more number of or continuously varying circulation along your wing. So that you are placing your vertex filaments like this from leading edge, so from the tip to root, you're placing your vertex filaments like this, and you will, by doing this, at every location, you are adding some kind of, for a small location, if you say, you are adding some kind of circulation, some small amount of circulation that is corresponding to d gamma. So if you want the circulation that is corresponding to here, then that is summation of d gamma 1 plus d gamma 2 plus d gamma 3. So you are varying the circulation basically by placing a more number of filaments like this on top of each other. So this is the line we are stating, this line, as we are overlapping all these filaments. This particular line is the lifting line. Okay. So this a lifting line is the primary concept that we are investigating, that how much of lift that we are going to that we already obtained in the theory, that in your course lectures. So let's see in this also how we are modeling the downwash or the velocity on the lifting line, and we are framing the entire induced angle of attack and angle of attacks equations, and then we will just see the final outputs of this induced angle of attacks and the lift coefficients and the induced drag coefficients, and how it is modeled is there are basically started in this theory. If you read that in the theory of the course, but this circulation distribution on the lifting line, it's a common to assume it is an elliptical kind of distribution on the lifting line. If you say this is your lifting line, in this lifting line, that your circulation that assumed as it is varying in a elliptical kind of pattern, and your movement in this direction is a y direction, so you will be having a minus b by 2 here and plus b by 2 here. So assume this is a elliptical kind of distribution. Then what we will get the same thing, that dw is equals to minus d gamma by the induced amount of because of a small element. If you consider any small element, and because of the circulation, the small gamma there, we will get by the velocity there, we can write it is like this, minus d gamma by 4 pi y naught minus y. So we wrote this, the change in circulation along the y, we need to first formulate that. This formulation, that we know that this is varying in a kind of ellipse format, but the entire the downward velocity or the velocity induced at some particular point y, how we wrote that, we wrote it by using the Biot-Savart's law. If you can go back to this, you can recollect this theory. We wrote this by using the Biot-Savart's law, and we need to multiply the small element, that is dy. If you take this is a small element dy, you need to multiply that dy with the rate of change of the circulation at that point, and then use the distance of 4 pi. This is a 4 pi from the y naught to y. This is how you will get the downwash induced by at the particular point. If you want to get the downwash induced at that particular point because of the entire circulation from minus b by 2, this is still the downwash induced at that point, but the thing is that we are looking at from the entire circulation that is varying from minus b by 2. So you just need to integrate from minus b by 2 to b by 2 along the y direction of the same thing. Okay, so now we just integrated. Once you did this integrated by assuming the profile of the circulation is an ellipse, the profile is also well formulated, that that you can, let me write the formulation, that is gamma of y, that how the profile is varying, this gamma of y is equals to gamma naught times 1 minus 2y by b whole square. In this aerodynamics, it is common for us that you assuming the circulation of a finite span wing is the circulation is varying in this elliptical formulation. So you can find the relation between the amount of your span and your y location. So that is how your circulation is varying. Once you done that, you will get the induced angle of attack. With this assumption, you will get induced angle of attack is, we know that induced angle of attack is the downwash by u infinity, and use this formula. Like this is the basic definition of this induced angle of attack. Once you substitute this thing, you will end up with any angle of attack, that actual angle of attack, or the geometric angle of attack, that you will end up with this a big equation like this, after using all this definitions, that the gamma definition, if you substitute in this d gamma by dy, and if you differentiate and integrate, once you are obtaining this w of y, you just need to substitute this w of y in this induced angle of attack equation, that a formal definition of it, and then you will end up with this big equation uh, for your geometric angle of attack. This is your geometric angle of attack, can be written like the entire format is I'm just writing. This is when we are dealing with the big kind of problems, we may need this entire information of the how the geometric angle of attack is just a combination of this part. This part is alpha induced angle of attack, and this part is alpha effective. So we need this combination to find the geometric angle of attack. So using this information, uh, lift per unit span, also we know that why we are doing this. We know that we have the target of finding the alpha induced angle of attack. Alpha induced is obtained, finally obtained that the alpha I equals to CL by, with this theory, we got pi AR, where we already seen that AR is the aspect ratio. And the corresponding induced drag, CDI is equals to CL square by pi AR. So this is the details we get. That is, induced angle of attack is alpha I, and induced drag coefficient is CL square by pi AI. So how we get this? So what is the possibilities of getting this? And that every details of the theory that you have already might came across the course content. I'm not going to those details. So induced drag, that we will get the lift coefficient from the Kutta-Joukowski theorem. That lift coefficient also you can find that by integrating the your gamma variation along the span. Based upon this only, because we know that induced drag coefficient di is a component of lift L alpha I. So if you want to get the induced drag component, just use this definition only, and then multiply the same, that we have substituted the L here. This is the substitution of L, and then you multiply this alpha I, and because we are integrating here, you substitute the same alpha I here, that's the induced angle of attack, you will get the drag coefficient, that is Pi. If you do the non-dimensionalize of the same thing, you will end up with the alpha I equals to CL by pi AR, and the drag coefficient, just drag coefficient CDI is equals to CL square by pi AR. So these two definitions are important, or these equations are important for us for solving the any kind of problems in the finite wing aerofoils. And also you will get L equals to in the dimensional format, L equals to gamma B pi b gamma naught rho infinity u infinity by 4. So this is also a useful format. Okay. So these all things you need to remember, that only applicable when we are dealing with the elliptical kind of distribution. But if you are having any other kind of elliptical kind of gamma distribution, the strength of the gamma distribution. But if you have any other kind of, suppose the distribution of the gamma is, if it is like this, if your gamma distribution of along the y direction is like this, you may need to use your Fourier transformation to fit, or the Fourier series to fit your this kind of function with the sine functions or the cos functions. So this comes in the generalized format of lift distribution calculation. These things are not valid there, but to make these things also valid, we have uh, some corrections in this kind of equations that we have derived so far, that just by assuming the Fourier kind of coefficients involving in the gamma functions, that is gamma of y is a function of some gamma of sine, and it's some kind of, let me write it clearly, summation I equals to sorry, 1 is to k a n sine of n some values that you will get. So we will get a more sine curve summation to formulate this entire. It's a summation of more sine curves with different amplitudes and different uh, wavelengths, different amplitudes and different wavelengths. That you combine those, you can formulate this uh, a kind of nonlinear or a linear or nonlinear kind of this gamma function. So this generalized function have also some solutions. Let's see that how the solutions are varying. Suppose if you want to see that induced drag coefficient, it will become like CL squared by pi AR and 1 plus delta, where this delta is the corrections that involves with the function. Delta is the delta of a naught comma a n, where these are the is a function of the Fourier coefficients that a naught and a n. So this is the some correction that involved when the gamma distribution is varying, not with the, not like an ellipse by or some other function. And the lift curve slope also affects in such a way a is equals to 1 plus a naught 1 plus tau by pi ar. We might have seen already that based upon the taper ratio CT by CR, your delta is the affecting parameter, where delta is this parameter. If you vary the CT by CR, the taper ratio also, this parameter also varies. And then this is the formulation for changing of the lift curve slope. If there A naught is for the lift curve slope for your aerofoil, and if you want to use the same for the lift curve slope for the finite wing, you need to use this kind of formulation that lift curve slope decreases for this finite wing and decreases by this ratio, that is 1 plus A naught times 1 plus tau by pi AR, where this tau corresponding to again your Fourier coefficient. This is not, it's a kind of correction then obtained from the Fourier coefficient for a generalized kind of circulation distribution on the wing. So these are the some basic details that about the finite wing that we are going to solve today on these concepts, and we will see some problems after a 10 minutes of break. Okay, so let's meet again at 7:10. Okay, thank you.
Okay, sir.
Okay. So welcome back to the session. I hope you are back to the session now.
Yes, sir.
Okay, okay. So let's start the next few questions so that we will solve and then we can wind up this session. Okay. This is recording. Yeah. Let's solve these questions. Some of the questions related to the concept that we just seen before the break. Okay, the questions are like this. The first question is again a true or false kind of statement kind of questions. In this, we have the aspect ratio of the wing is defined as the ratio of wingspan square to the chord length squared. So we already just learned the aspect ratio is not this one. The aspect ratio is actually the wingspan squared by the platform area, that is S. So that is B squared by BC, that is the ratio of B by C. So this is not the correct answer. And the second statement we have is lower aspect ratio makes the finite wing have aerodynamic characteristics closer to the airfoil section. We also see in the theory that if the airfoil is having a lower aspect ratio, the effects of wingtip vertices are much severe than your uh, uh, than your long span kind of wing. If you have a very long span, the wingtip effects are not much severe in the mid section. So they will end up here with and convect away from to the downstream at the tip itself. But if you're having very low span, these effects are severe on the entire aerodynamic characteristics. So the second statement is also wrong. So both the statements are false in this case. Okay, so let's go to the next question. In this question, we have which option is correct for the following statements. We have some statements here again. So the statements are like this. The total drag on subsonic finite wing in incompressible flow is sum of skin friction drag, pressure drag, induced drag, and wave drag. We have a subsonic finite wing and a subsonic finite wing, and the flow is incompressible. Skin friction drag can be possible because he did not mention whether it's inviscid or viscous flow. But pressure drag is also common, and induced drag is also possible because it is a finite wing. But the wave drag is not possible because it is a subsonic kind of flow. Okay, the first statement is false. The second statement is the total drag on the supersonic finite wing inviscid flow is the sum of skin friction drag? No, because it is inviscid flow. And the pressure drag? Yes. And induced drag? Yes, this is the finite wing. Sorry. And the wave drag? Yes, because it is a supersonic flow. So this second statement is also false because it includes skin friction drag. So both the statements are false. Okay. And let's go to the next question. In this question, we have a simple problem that is consider a finite swept back wing. In this finite swept back wing, the aspect ratio swept back or swept wing, they just mentioned it, and the aspect ratio is 8, and the tip chord is 7 feet, and the root chord is 8 feet. Determine the taper ratio. We have additional information in this question, and but we only need to find out the taper ratio, that is tau equals to CT by CR, the ratio of tip to root 8 by 8.75. And if you solve this, you will get uh, 0.8 as the taper ratio for this problem. Okay, let's go to the next question. So in this question, we have um, velocity at a point 6 meters away from the semi-infinite straight vertex filament having a strength of 1675. Okay, we have a velocity at some point that is 6 meters away from the semi-infinite vertex. Let's take a semi-infinite vertex. Suppose this is a semi-infinite vertex and this is tending to negative infinity or positive infinity, and you have a point at 6 meters away from the semi-infinity vertex. That the velocity at this point, sorry, we need to calculate the velocity at this point, but the strength of this vertex will be the gamma equals to 1675 meters square per second. So from the Biot-Savart's law, we already know that how to calculate the velocity induced at a point with a semi-infinite vertex or the finite other infinite vertex. The formulation is like this. Uh, Let me write the correct format of this. The velocity induced from the semi-infinite vertex from the Biot-Savart's law, you can write it as v equals to minus gamma by 4 pi h, where h is the distance, perpendicular distance from your axis to the point at the distance. So this velocity now we can calculate by simply substituting this all these parameters, that is minus 1675 by 4 pi times all the units are in same condition, so you can directly substitute that, and once you solve it you will get velocity equals to, this will be also comes as a minus 22.22 meters per second, but they're given in the absolute format, so this is your correct answer. Okay, let's move to the next question. So in this question we have question number 5. Consider a finite wing with an aspect ratio of 8. So this is a finite wing we have, and here the aspect ratio is 8. That is b squared by s, or it is b by c equals to 8. And the circulation varies elliptically. Note that the circulation is varying elliptically along the span of the wing. Okay. And the lift coefficient CL is 0.45, and what will be the induced angle of attack and drag coefficient at the mid span of the wing. So we need to calculate the induced angle of attack, that is alpha I, and drag coefficient CD. See, induced drag coefficient CD is we need to calculate. We from the theory that we are already just covered in the previous session, that we got the two important formulations like this, that alpha I, induced angle of attack, can be written like CL by pi AR, because it is circulation formed in the form of elliptical circulation. Then induced angle of attack C alpha I equals to CL by pi AR. Okay. And then induced drag coefficient CDI equals to CL squared by pi AR. Now let's substitute the same thing to solve for the induced angle of attack. The induced angle of CL we have is 0.45 by pi times aspect ratio is 8. So once you substitute it, you will get 0.0179. It is in the radians format, so we need to convert into the degrees. So just multiply with 180 by 5, you will get 1.03 degrees. This is the induced angle of attack. And then the induced drag coefficient CDI equals to CL squared by pi R, right? So CL square, that is 0.45 square. We have the CL equals to 0.45, that is the given data. And the same thing, we can just need to multiply it, then you will get the induced drag coefficient is 0.008. So this is your solution. Let's go to the next question. So we have question number 6 here. The question number 6, they are asking for the direction of the flow that crosses the top surface of the wingspan is. So this question also we discussed previously, that this question is stating that what is the direction of the flow that crosses the top surface of the wingspan. That is from the top span, that from the wing tip to root of the wing, the flow crosses the top surface. So if we see in this question already in the previous session, so this is the option is from the wing tip to the root. Okay. And coming to the next question, this question states that the local relative wind differs from the free stream velocity. Let's read the question once again. The local relative wing differs from the free stream velocity by a certain angle for a finite wing. This angle is known as induced angle of attack. Let's read what is actually they are asking is, suppose if you have a local relative wind differs from the free stream velocity, okay, by a certain angle. Okay, the local free stream angle or the geometrical, it is strikes in the geometrical angle of at a direction. Okay, so when you are this local free stream velocity is meeting with the downwash, that is W, you will see a difference in, sorry, you will see a difference in change in angle of attack, that is downwash in this direction. So when you see this change in angle of attack, what is that particular change in angle of attack that we say it is an induced angle of attack that we discussed in theory session. Okay, and then let's go to the next question. So all these questions what we have discussed so far are all the true or false kind of statement or based upon the theory that we have discussed so far. Some problematics also we see. And let's go to the next question. This question is also true or false kind of question. We have the, which option is correct? A component of the lift for a finite wing generates induced drag. What we are asking here, the statement one, a component of the lift for a finite wing generates. Yes, this is true. Actually, a component of the lift for a finite wing generates the induced drag, because we seen that from the vertical line, if you draw a line, and from this, the lift tilts some particular angle, that is alpha I, that is induced drag, and this component we call, this is the lift induced drag, that is di. We say it is a lift, and that this is the component that is generated because of this tilt in the lift in the drag direction, that we call as a induced drag. So that is what they are asking here, the component of the lift. So the second one is, local lift is inclined to the vertical for a finite wing due to the induced angle of attack. This is also correct. The same thing that they asked in another way. So the both statements are true in this question. Okay, let's go to the next one. And which option is correct for the following statements? So let's read. This is also true or false kind of question. The statements are like this. According to the Biot-Savart's law, the circulation along any path encircling a vertex filament is defined by the vertex local strength. It is more or less looking like a correct statement, but the thing is, it is not correct, because the circulation along any path encirculating vertex filament is not defined by it is a vertex local strength. It is a complete strength of the vertex that we say, that is a gamma. If you take about any path along the vertex filament, and if you find out its strength, the circulation is always constant. That is what and we learn in the Biot-Savart's law. So it is not on the vertex local strength. It is a constant everywhere along the vertex filament. Okay, so the first statement is false. And the second one is, there is no such thing as a curved vertex filament. No, this is also false, because curved vertex filament, vertex filament can be curved, straight, or anything. Okay, so the both statements are false in this question. The next question, that according to the Brandy lifting line theory, a finite wing is analogous to. This also we discussed previously about the assignment questions. It's a kind of repetitive questions also. So we seen that according to the Brandy lifting line theory, he tried to first model the finite wing. In his theory, he stated that the finite wing is in the form of the horseshoe vertex. By placing a filament, vertex filament on the finite wing, and to making it end in the uh, to make it end in the fluid domain, he make it as a trailing vertices also. So sorry. He make it as a horseshoe vertex, but for making it as a finite wing analysis, he started with its theory by assuming the finite wing as a bound vertex, as in the form of the bound vertex. That the complete theory or the we discussed earlier. This is not though the lifting line theory is started with the horseshoe vertex, but the Brandel theory of this lifting line is by assuming that wing is in the form of a bound vertex. Okay, yes. So let's go to the next question. Here we have a problem here. The problem states that a finite wing with a general plane form geometry has an aspect ratio of 7. Here we have aspect ratio 7 and the taper ratio of 0.6. We have a 0.6 taper ratio. The wing has thin symmetric airfoil section. The airfoil section is very thin. Okay. And what we are stated to ask is it is a thin airfoil section. Determine its induced drag coefficient at an angle of attack of 6 degrees and assume that tau theta. These are we already seen that in the previous session that tau and theta are the corrections when if we don't have the elliptical circulation along the lifting line. So these correction values also given in this question. So it is not an elliptical lift circulation distribution on the lifting line. So let's calculate the induced drag coefficient uh, at let's calculate the induced drag coefficient at angle of attack 6 degrees and also uh, what else? Only the induced drag coefficient they asked for to calculate. So induced drag coefficient we have CDI equals to CL squared by pi AR with a correction of 1 plus I think it's delta. Let me verify that the correct statement. Yes, induced drag coefficient is CDI CL squared by pi AR plus 1 plus delta. This is the correction coefficient for the function of Fourier coefficients. And then we need to find that CL also. We don't have a CL here. How can we can find the CL? CL we need to find it. Alpha is equals to 6 degrees. So CL equals to this is A. A denotes your lift curve slope. A times alpha. So how you can find the A for a finite wing? For a two-dimensional airfoil, A naught we have that 2 pi. If you want the CL at for the A naught or for a two-dimensional airfoil, you can write A naught into alpha, that is 2 pi alpha. You can get the CL for the two-dimensional format. But if you want for this A for what for this finite wing, you need to use a correction again. That is A equals to A naught by 1 plus A naught by some pi AR, and additional correction is also there. Let me see that. Yes, this additional correction is 1 plus tau. So this correction also we have, and this also we have. So we have it, and we know that A naught equals to 2 pi for a two-dimensional airfoil at for a lift curve slope. So let's substitute that A naught equals to 2 pi that I'm substituting here, and we have the aspect ratio of the wing is 7. So let's substitute that aspect ratio of the wing also 7, and the tau we have 0.055. So this is your A value. Once we solve for this A value, we will get 4.828 by radian. This is per radian. And if we solve for the degree, this will be 0.084 per degree. Okay. So this is your uh, lift curve slope for the finite wing. Once you get this lift curve slope for the finite wing, you may need to solve for the CL at this particular angle of attack of the finite wing. That is CL equals to A times alpha. That is A equals to we have 0.084, and then alpha we got is the 6 degrees. We use the same lift coefficient in the degrees format only, the lift coefficient slope in the degrees format only. So 0.084 into the 6. So this will give you CL equals to 0.504. So once you get the CL, what we need to do, we just need to substitute back into this induced drag coefficient formula. That is CDI equals to CL equals to we have 0.504 square by pi times aspect ratio is 7 times 1 plus delta is 0.055. Okay, this is the square, I think. No, 1 plus delta, sorry. Go back. This is 1 plus delta, not square. So this is 1 plus delta, and if you simplify this, you will get the induced drag coefficient CDI equals to 0.012. So that's how you can find out your solution. Well, first you need to get your CL formulation for CDI, and we must ensure that it is not an elliptical circulation distribution. So you will get some corrections also, and then you need to use those corrections, and then you need to find the CL from your theoretical two-dimensional aspects, and there you can get your induced drag. Okay. Let's go to the next session. Next, last question. In this question, it is also kind of true or false kind of statement. The question is like this: which option is correct for the following statements? For a delta wing, the value of maximum lift coefficient, we are having a delta wing here. For a delta wing, the value of maximum lift coefficient is higher compared to the airfoil, compared to its corresponding airfoil section. This is not correct. If we see the delta wing lift characteristics, let's plot the delta wing lift characteristics. The stall angle of attack of the delta wing is around 25 to 30 degrees, so which is like this. But the CL is always minimum when compared to your airfoil cross section. So the first option is wrong, and the stall angle is much higher in case of delta wing. Much higher in case of delta wing compared to the airfoil. Yes, this is true. So the stall angle is higher for your delta wing coefficient, and where the maximum lift coefficient is less for your delta wing. So the first option is false, and the second option is true. So these are the few questions that we discussed in this session. So then we come to end of our session, and I would like to take any few questions if you have today's class, or anything that you want to discuss regarding these concepts. Arihit?
Yes, sir.
Okay, I hope you have any questions you want to discuss.
No, sir.
Okay. Okay, if no questions, let's have a common discussion on this aerodynamics. So how far you have covered the lectures that you have listened so far? Can you explain, shall we discuss that what is happening in the present session of your discussions? The lectures that you have listened?
Yes, sir. Actually, I have watched up to the last, means I have missed the last week lectures. Before that, I have watched
Okay,
week 7. And today, sir,
okay.
you are talking, you are means discussing about the lifting line theory, Prandtl lifting line theory. And
Hmm.
in earlier of the session, you discussed about the airfoil series, the 4-digit NACA series, in which uh, how to identify the numbers, as well as how to find the aerodynamic center. And uh, sir, you were discussing about that elliptical distribution also in case of elliptical distribution in case of
Hmm.
lifting line theory, and
Hmm.
why bound vortex does not exist means single means it is ending or it is completing to trailing vortices. And also the concept of induced drag, in which the wingtip vortices plays a major role
Hmm.
to reduce the induced lift. So to reduce the lift and the angle of attack.
Okay, these are all
Uh,
very good. Let's have a small discussion in such a way that I would like to ask, like, what professor has covered in the professor, not my lectures, what professor has covered in your last week session, that maybe importance of CFD or numerical methods that he discussed, and after that, did you learn any other new concepts?
no, sir. After means in lecture week 7. I have covered up to week 7. After that, I missed week 8 due to my exams. So, sir, in
Okay.
week 7, professor discussed about the CFD and the procedures of CFD, like panels method, discretization, and all. So he discussed about all these things and how color coding means after CFD analysis, how color coding is used, means what is the preference for which color is used for boundary layer and which color is used. So he has just give a overview of that and other like panels method, then vortex. I'm forgetting the names. Vortex.
Okay.
That methods he has discussed, and he has just took up few names like that Rans, Reynolds averaged, that method. So in those lectures he just gave a overview of how CFD is used for analysis
Okay.
of airfoils.
Okay. So you have done some CFD also in ANSYS Fluent, right? You have you
No sir,
simulated any kind?
no sir. Sorry.
Okay. Can you like any experience with the ANSYS Fluent you have?
No, sir, I don't have any experience, but I'm in learning stage. I'm also trying to learn ANSYS Fluent,
Okay.
but I
You
don't have
can
any.
just okay. You can start learning the ANSYS Fluent and you can use simulations also. How to do some kind of simulations in ANSYS Fluent that will be useful for you. And let's discuss in some particular concepts like uh, if you want to model an aerofoil, like
Yes, sir.
if I assume you are an engineer and you want to not model, you want to simulate an aerofoil, and how will you, where you will you start first? You want to simulate an aerofoil, where will you start? Simulate in computer or maybe in theory? Just assume you are like an engineer and you will give your aspects. That's it. You want to simulate an aerofoil, its characteristics. You can take any method, any methodology, everything. You just need to. Your ultimate goal is uh, plotting the lift coefficient with respect to the angle of attack. How will you approach? This is your question.
Yes, sir. So, means after watching the videos and gaining some knowledge, I think, sir, it can be done in two ways. Means before CFD
Okay.
has came into existence, engineers used to do it in theoretical mod using theoretical model like RANS or panel method. So after
Hmm.
CFD, according to me, sir, I would start using CFD, and from that I will try to model the airfoil as per the
Hmm.
requirement of the lift to drag means coefficient of lift and other
Hmm.
requirements. So according to me, sir, I will start with CFD first. So
Okay.
CFD, I will follow the methods which are being discussed by in professor's lecture, like discretization. First, we have to find out the objective, and then we have to follow the other methods like
Hmm.
discretization or and analyzing it, and then we have to perform the CFD in any software. Like for example, sir, we can take ANSYS Fluent
Hmm.
for analyzing it, and then the data generated in ANSYS Fluent will give us the results whether our approximation are right or wrong. As per me, sir, I think this is the method for doing any CFD analysis, but I don't know whether it is correct or wrong.
Okay. That is all right. But okay. I'm getting an echo. Wait. So now, if you are an experimentalist, then you just said everything in a theoretical perspective. Now, if you are an experimentalist, how will you proceed? That you want to find out an experimental way.
Sir, in
Suppose
experimental,
just one more question. Like, is it just for your clear understanding of aerodynamics? I'm not questioning you, or it is not any kind of mark session or nothing. We just discussing about this aerodynamics that we have learned so far. So whatever your understanding, you just tell from that perspective only. Suppose, are you able to see this? I don't know whether you can see it or not. Are you able to see
Yes,
the
sir.
cross?
Yes, sir.
i-
Yes,
Is
sir. I
it a
can see it.
airfoil cross section?
Yes, sir.
Okay. Suppose this is assume it is an ACA 0012 aerofoil. This is an aerofoil cross section. Is it clear for you? Are you able to see this?
Yes, sir. Yes, sir. I can see it.
Okay. So this is an ACA 0012 airfoil made with some teak wood, and you have this span. The span is this much, like say three times of chord. Now, what is the aspect ratio? You can say if it is three times the chord. The span
It is
is span is three times the chord.
okay, sir. First of all, according in the formula of aspect ratio, I think it was given wing planform area divided by uh,
Hmm.
uh, b square. That is the span. Uh, B square is the span of the airfoil. That is this. And in case of infinite wing, I think it is B by C.
Yes.
Means I am recalling it, but I am
Hmm.
not sure that whether it is correct.
Hmm.
Uh, so, sir, can you just repeat the
It-
question? It is three times the chord length.
what is the three times the chord length? What is its aspect ratio?
As if, means the wing planform area is three times the chord length.
The span chord length is C, and the span is three times the chord. Span means this tip to tip. This tip to tip, this is span,
I
and
got
this
it,
is
sir.
my chord. And what is my aspect ratio now?
I think it will come 3b into c. If we can 3bc, I think, sir.
3b by c, not 3b by c, 3c by c. It will
Yes,
come as 3c by c. So the aspect ratio is 3. Okay. Now
yes,
let's
sir.
let's think in the engineer's perspective. Suppose this is a random airfoil I given with you. Like you don't know its characteristics. This is just a random airfoil I given to you, and
Yes,
I just asked you. You just find it in any kind of way that you find out what kind of airfoil it is. So what will you do to identify what airfoil it is resembling, and whether it is NACA 4 series or 5 series? That is your perspective. So what are the basic things that you will measure in this airfoil? It's a random aerofoil. You don't know its characteristics. So what will you measure as in an engineer's perspective?
yes, sir. First
What,
of all, I think we should measure the chord length.
okay, we
Uh,
should measure the chord
and
length. Yes.
span of the airfoil, means span
Span
of the
of the
wing.
aerofoil. Okay.
And so after that, to identify whether it is NACA 0041 or the airfoil you said, I think we
Hmm.
can calculate it from the formulas uh, of the camber thickness in hundreds, and uh, I'm not getting, sir. I just can't recall it right
Yeah.
now.
Okay. You need to identify first whether it is a symmetric airfoil or asymmetric airfoil, right?
Yes, sir. Yes, sir. That we have to identify first.
Yeah. So how can you identify by looking at just a shape?
Yes,
Like
sir.
now,
If we want to understand whether it is cambered or symmetric, we can just look at its shape. If the camber line is merging with the chord line, then we can say that the airfoil is a symmetric airfoil. If there is
hmm.
a difference between the camber line and chord line, then we can easily understand that it is a cambered airfoil by looking at the airfoil.
Okay, then how will you measure its camber and maximum camber location? Experimentally, if
Camber
you
and
want to do it experiment, how will you measure its camber and maximum camber location? Just think in an engineer perspective way, that's it, but not in a questionnaire or exam kind of perspective. You are an
Okay,
engineer
sir.
and you are trying to measure it. What will you do?
Sir, I don't know whether it is which kind of airfoil. There is no information given, right, sir?
Yes, there is no information given. You need to measure its all characteristics according to NACA 4-digit series.
Sir, if I am not wrong, then if we means, uh, carry out experiments on this airfoil, and if we uh, can guess the center of pressure or if we can guess the aerodynamic center, and from that aerodynamic center, if we try to solve it, whether, sir, is it possible, sir, like in that way? Because, sir,
It's possible, but first you need to find what aerofoil it is, right? You need to find what aerofoil it is. How will you do that?
don't know, sir.
Okay. If you want to find out what aerofoil it is, you need its measurements. But those measurements I did not give you. But if you want to check it what kind of aerofoil it is, you need to take a graph sheet. You need good graph sheet you need to take and place your graph sheet like in a horizontal way, and you place your wing on top of the graph sheet, match your origin with your leading edge, this leading edge, and you place your origin accordingly. Okay. And then you mark the points. You just mark the outer surface of this aerofoil. So now what you did, you just transformed your this aerofoil chord or aerofoil outer shape onto your graph sheet. Got it?
Yes, sir. Got it.
Now you have the all coordinates of your aerofoil, the actual aerofoil coordinates on your graph sheet now, right? So what you need to do, you just next divide the some points along your chord on the graph sheet. Along your chord, you need to divide the points in the graph sheet, and you need to find like divide the points and join the lines from top upper surface to the bottom surface, like vertical lines. Draw your vertical lines along this chord. Okay. Once you draw the vertical lines along the chord, and you just need to mark the points of middle points of the all these vertical lines. If the airfoil is symmetric, you will get the same line of your chord. If the airfoil is cambered, you will get all these middle points. If you join all these middle points of the vertical line, you will get the camber line of the aerofoil. Got it?
Yes, sir.
Yes. And then
Sir, I
there
can
is your
just can you just repeat that middle portion, sir? I just can't visualize it. You first of all, sir, you are taking vertically over a means above a graph sheet. We are placing it, and we are just plotting it with a pen or pencil on that graph sheet. And sir, after that, what
yeah,
you told, mm, how
yes. Let
to.
me share this. Let me share this. Okay. Can you see my screen?
Yes, sir.
So you just drawn your airfoil outer coordinates just by placing your airfoil on the graph sheet, and the graph sheet origin, main origin is like this. Okay.
Yes, sir.
This is your x-axis on your graph, and this is your y-axis. This is your origin, and this is your tip, leading edge and trailing edge. Okay. So now this is your graph sheet. What you need to do
Hello,
is you
sir.
need to do. Yes. Can you hear me?
Hello.
Yes. Can you hear me, Arhit?
Hello,
Hello.
sir. You
Am
are
I
not
audible?
audible.
I can hear it. Arhit, can you rejoin once again? Hello. Is it audible?
Sir, you are not audible. I can't hear you.
Okay, okay. Can you
Hello.
rejoin again? Am I
Hello.
audible now?
Hello.
Hello?
Sir, am
Arhit, you're audible. You're audible.
hello, sir. You are not audible.
Let me check where is the problem.
Hello.
Hello? Is it audible now? Am I audible now? Arhit? Hello?
Hello?
Am I audible now? Hello?
Sir, you are not audible. I can't hear you.
Okay. Let me join again then once. Am I audible now? Can you see my screen? Am I audible now?
Hello?
Yes, Arhit, can you hear me?
Yes, sir. Yes, sir. Yes, sir.
Okay. So what you need to do is you just need to um, so you need to plot your graph like this, and you need to mark the divisions that is perpendicular to your y-axis, x-axis. So you need to mark some divisions like this. And if you can able to join the middle lines, suppose these are your coordinates. So you need to join the middle lines of it, all the middle lines of this vertical lines. Once you join all these middle lines, this is your camber line. So the maximum value in this camber line from your chord will give you a maximum camber, and its location from the leading edge will give you a maximum camber location. Okay. And this is your max camber. And this is how you can generalize any kind of aerofoil using the NACA 4-digit series. This will be useful for your experimental analysis or any aerodynamic analysis later on. Got it?
Yes, sir. I got it. Sir, it is quite interesting how you told this. Means I have never thought like this.
You
To
need to do all this
identify.
kind. Yes, you need to do all these kind of things in your internship.
Yes,
Some
sir.
more advanced kind of things also you may expect it, to do soon. Okay.
Okay, sir.
So regarding, let me stop this thing. Sharing.